Our next big hill to climb with these integrals is some of the basic integration rules, or the basic integral rules. Now, again, there's some more notation to happen here. So recall, one way to write this, one way to write the derivative is you could say if f of x is equal to, let's say, x to the second minus 3x, then f prime of x can be written as 2x minus 3. We're used to that. But we can also combine this into one statement. Rather than having to say this is the original function and this is its derivative, we may use the Leibniz notation, which says this. All right, so see what we have here? It's the same information, but it's in one line instead of two. This says the derivative with respect to x of this function is equal to that function. Now remember, when we write this, the following is not correct. This does not equal 2x minus 3. Why is this correct but this not correct? Well, you might say, well, obviously this has the brackets. This actually does have meaning. This is wrong. That is not equal. This does not equal that. What it does equal is this. What's the derivative of x squared? This derivative, this differential operator, applies only to the factor immediately behind it. This d by dx does not apply to the 3x. And so the derivative applies to this. This is 2x. That part's correct. But this has do nothing. This is negative x. This is correct. This is not. And so the moral of the story is this. If you want this derivative to apply to the entire function, multiple terms, you need to have it grouped together. That's going to come into play when we start using these integral symbols. All right? So, back to the basic. We may either write with 2 lines or we might write with 1 line. All right? So, rather than say this, we can say this. If, you recall that if f is a function, its antiderivative is capital F. Is that right? Yeah? Just like if this is f prime, the antiderivative is f. So we can say this. If f prime, well, let's say it this way. If little f is given to be, let's say, let's get off the f schneid. So now we have little g. What's the antiderivative of lowercase g? Is clear it's going to be capital G. So this is the derivative going downward. This is the antiderivative going upward. So if g of x is given to be, let's say, 6x minus 2, then we may find the antiderivative. This is the antiderivative process. Add 1 to the exponent. Divide by the exponent you just created. What's 6 divided by 2? Reattach the variable. Which variable do you reattach? We reattach the x. See how everything's coming together. Reattach the variable, in this case is x. And then we need the constant of integration. So it's correct to say if little g is this, capital G is this. But there's a more concise way to write this. We can write integral symbol just like we had before. This needs to be grouped together. Either parenthesis or brackets is irrelevant, but grouped together. All right? We're doing integration. This is the function upon which we're going to operate, and this is the variable indicator. And now we do the same process. Add 1 to the exponent, divide by the exponent. What's 6 divided by 2? we have added 1 to the exponent, reattach the variable, this tells us which one, and throw in the constant of integration. So, you can say this expression in 2 lines, or you can say this expression in 1 line. You can say this expression in 2 lines, you can write this expression in 1 line. This is typically the procedure we will use. This is the notation we will use going forward. Now, one more thing on this constant of integration. The quickest way to lose 1 point on anything you're working in calculus is to forget the constant of integration. There's not an instructor on the planet that's going to let you get by leaving out the constant of integration. All right? Make sure you use the constant of integration. Make sure you don't forget, whatever it takes. I actually had a student one time during the course of the class, he kept forgetting to write plus C. He just forgot to write it every stinking time. And he was like biting nails. He was so upset with himself for forgetting it. He knew he was going to forget it, so he doubled his efforts to remember, and he still forgot it. So one day we were having a quiz. This is several years ago. One day we're having a quiz with several of these integrals on it, and he came in and he showed me his hands. I said, okay, what's the big deal? He says, look, there's nothing on my hands, and he was right-handed. So he took his pen and he wrote on his finger plus C. He wanted me to know that he wasn't bringing notes into the quiz. He was actually writing the notes on his finger. So he wrote on his finger plus C. So whenever he was writing, he would see plus C right in front of it and remember it. So that was fine by me, and from then on out, he got it perfectly. I'm not saying you need to do that, but you do need to remember the plus C. You have to remember the constant of integration. What happens is students learn it so well, they start to overlearn it. They start to put plus C where they don't need it. Be careful. You don't need to do that. I have had students where they're signing a legal document. They sign Mike Evans plus C or something. So you do need to include the constant of integration when you do the antiderivative. Don't forget to do it, and do it only when you need it. We will talk later about the procedure for finding it, determining the constant of integration. That's a separate issue we're going to worry about later on. But for now, write it correctly and make sure that you understand the process. Now, notice that what we've done here, everything we've worked with so far is working with the power rule. And so we're going to make that a little more official. Just like we have differentiation rules, we also have integral rules. In fact, if you have the function f and you use the derivative rule to find f prime, that means if you have f prime, you would be using the antiderivative rule to get back to the original function f. So anywhere you have one of these rules, now think on our basic form sheet, think of all the rules for the derivatives we have. The derivative of tangent is secant squared. Well, now you know the antiderivative of secant squared. If you know the derivative of tangent is secant squared, what's the antiderivative of secant squared? I know what you're thinking. You're thinking it's tangent. The antiderivative of secant squared is not tangent. It's tangent plus c. You always need the constant of integration. If the derivative of sine is cosine, then the antiderivative of cosine is sine plus c. Anytime you have a derivative rule, and so for all of the derivative rules, essentially, we're not going to pitch all of them in this language, but for essentially all the basic forms, there is an associated antiderivative form or an integral form. And so this is going to be a collection of them. If you have your list of basic forms, you're going to see these incorporated into your list of basic forms, what you'll be held responsible for. So, a couple things. In no particular order, this is the antiderivative of x raised to the n. We've talked about this already. This is the basic power rule. Our rule was, what did we do? The integral of x to the n is x to the n plus 1. Now, the coefficient here is 1. So we divide by 1 over, or we can put this in the denominator. You divide by the exponent you just created, plus the constant. So this is the basic power rule. So let's use that in several examples here. Let's go x to the 4th dx. Let's go the integral of y to the 3rd dy. It doesn't need to be y. The integral of t to the -3 dt. The integral of x to the 1/3 dx. Add 1 to the exponent. Divide by the exponent you just created. Throw in the constant of integration. This is with respect to y, so we're correctly working this. This is y. Add 1 to the exponent. Divide by the exponent you just created. Constant of integration. If all you're being asked to do is find the antiderivative or evaluate the integral, if all you're being asked to do is that, then you do not need to simplify this. If you need to simplify it for some other reason, that's a separate issue. If all you're being asked to do is find the antiderivative or evaluate the integral, then all you need to do is find the result, put a box around it, and be proud of it. Add 1 to the exponent. What's -3 plus 1? -3 plus 1 is not -4. You must do the arithmetic correctly. -3 plus 1 is -2. Divide by the exponent you just created. And add the constant. Add 1 to the exponent. 1/3 plus 1. 1/3 plus 3/3 is 4/3. Divide by the exponent you just created. Now, we know this. What's divide by 4/3? Multiply by reciprocal. Divide by 4/3. Is probably not asking too much to throw that in. Strictly speaking, I would give you this, but is it clear this is what happens? You multiply by the reciprocal, so that instead of divide by 4/3, it becomes 3/4. All right? Power rule applies to fractions, applies to negative numbers, applies to positive numbers, it applies to whole numbers, it applies to decimal values. Power rule applies for a wide variety of values. Now, one small detail. All right, apply the power rule. All right, you think you know it all? So, -1 plus 1, it's not -2, what's -1 plus 1? That's 0. Then you divide by 0. And the problem is, do you see this? You're not allowed to divide by 0. So this is not correct. Because you're not allowed to divide by 0. The power rule always has a disclaimer. If n does not equal -1. We will talk about that later in the semester. So the power rule works for any value for the exponent unless that value is equal to -1. Then it does not. So the power rule does not work in that one scenario. Power rule. All right. Suppose k is a constant. K is a constant. I don't want to use c because I'm going to use c later on for my constant of integration. So I'm using k for my constant. Pretend you're in German class. K for the word constant in German starts with a k. Constant. Remember our rule for the derivative of a linear term is you lay aside the variable, remove the variable. The antiderivative of a constant term is you reattach the variable. Which variable do we reattach? The variable indicator comes to play here. So this is you reattach the variable and add the constant of integration. That's why I didn't use c to start with here. All right? So the antiderivative of a constant is you reattach the variable. All right? All right? Suppose we have a constant times a function. What would be a specific case? Do we need to do, I think we've done several examples of this. This is straightforward. We'll walk through several examples of that. That's, I think, straightforward. But I do want to pitch this a little bit. So, right, suppose the constant is known to be 10. Suppose the constant, in this case, the constant is 7. And so on. There's nothing magic about 10 or 7. They can be, here, let's suppose the constant is -3 x to the 5th. I'm just picking numbers out of the blue sky. What do constant multipliers do? Hopefully I've infected your mind enough to know that that you're thinking in your mind, constant multipliers multiply along. Constant multipliers multiply along. You can almost hear it, the students themselves moaning it. The constant multipliers multiply along. Well, the same thing happens here. The constant multiplier, the integral of a constant times a function, instead of multiply first and then do the integral, what this property says is this. You may first compute the integral and then multiply by the constant. I don't know why I've shifted from K to A, but I have. My constant is now A. The specific letter you choose to represent the constant is irrelevant. But what this says is, you may, if you wish, multiply constant times function first and then do the integral, or you may do the integral first and then multiply by the constant. Now, if all we do is apply this rule, what does it say we get to do with this 10? See, A is being played by 10, f of x is being played by x to the 4th. So what we may say is, this is equal to 10 times this integral. Right? What may we do here? Right? We may move the 7 in front of the integral. Right? What may we do here? We may move the -3 in front of the integral. Now, sometimes students want to know this. Notice in this rule, we have a plus c. In this rule, we have plus c. We have constants of integration here. Students want to know, why don't you add the constant of integration here? And the reason is this. In this problem, we actually computed the antiderivative. In this problem, we actually computed the antiderivative. Anytime you actually compute the antiderivative, you need the constant of integration. But here, I have not yet found this antiderivative. Look what we have over here. We have not yet done the antiderivative here. All we're saying is the integral of constant times function is equal to constant times integral of function. This is integral of constant times function. This is constant times integral of function. So anytime one of these properties says integral is equal to this is a property that says here's how you evaluate, this is the technique for evaluating. This is how you evaluate the integral. When you evaluate this integral, you get this. When you evaluate this integral, you get this. Whenever that's the procedure, you need the constant of integration in that form. But this is not saying that. This says this integral and that integral are equal. This integral is equal to that integral. When you actually do the computation, that's when you would throw in the constant of integration. If we were to take this the next step, then we would say this is 10 times x to the 5th divide by 5. Then you would add the constant of integration. Look at this x larger here. Now you include the constant of integration. But we have gone beyond what this property is actually telling us to do. Now, to get from this step to this step, we applied this rule. And then to get from this step to this step, we applied this rule. And so that's why in this scenario, if you have integral is equal to integral, you don't need plus constant. If you have integral is equal to this expression, then you need the constant of integration. The key is integral equals expression or integral equals integral. In this scenario, no constant. In this scenario, you do need the constant.